Hello Honors Physics students, please have your handwritten notes open, and if you haven't yet printed out the Snell's Law activity from the Google Classroom post, please have that printed out and in front of you as well. So in class, what we do next is do some more demonstrations with diffraction and interference. In a previous video, I'd already shown you what happens when you send polychromatic or white light through the diffraction grating. You see we separate it out into the whole color spectrum, with the red diffracting to the side the most and the violet diffracting the least. And if you compare that to our chart of the wavelengths, we know that the red has the largest wavelengths and violet has the smallest wavelengths, and so we showed that the larger the wavelength, the larger the diffraction angle. Here are some images of what it would look like if we send monochromatic or single frequency light through different openings. This is mimicking what I would do in class. I would send the red laser light first through the double slit. This is, remember how we originally proved light was a wave. This is the pattern that we saw on the screen, and some of you were kind of far back in class, maybe you couldn't quite see it as well, but this is what it looked like. Even in the blob in the middle were a whole bunch of bright spots, and then the bright spots continue all the way out to the side. The bright spots are separated by dark spots, and this showed that repeating pattern of bright, dark, or constructive, destructive interference. This happens because light's going through two openings, and each opening has the light diffracting, spreading out in all directions, and those wavefronts overlap each other, creating this pattern of interference. Bright, dark, which is very similar to the soft, loud pattern we saw for the sound, and this proved that light was a wave that diffracted and interfered. What's interesting is if you send the light through a single slit, we get a little bit of a different pattern. In the blob in the middle, that is just one big bright spot. Next bright spots are over here, and then they diminish in intensity very, very rapidly. So yes, these get less and less intense when you go to the side, but for the single slit, there's so much more light energy in the middle and a lot less for these other maxima of intensity. There are some over here as well, you just really can't see them very well. You see that there's a lot more light in the middle, and also this is one big blob that's very, very wide compared to the size of these ones. In fact, this is about twice as wide as either of these on the other side, whereas all these bright spots are just about the same size, and they're kind of evenly spaced. And those are just the differences in the patterns there. Now, why does this happen? Well, it actually sort of goes back to Huygens Principle. So you may want to go back in your notes and review Huygens Principle. Also might be a good idea for you to go back to the virtual ripple tank, and on the upper right-hand corner, access the menu for either the double slit diffraction or the single slits, so you can see it happen. I'll show you some static images of it, but it'd be really good if you do it there for yourself as well, and I'll repost the link to that virtual ripple tank on our Google Classroom. So this is what it looks like for the two openings, the double slit. You access this part of the menu here, and you see that the waves are overlapping each other. Where it's solid, that's where they're constructively interfering. Where it's grayed out, that's where it's destructively interfering. This is where, if you're going in a straight line across, if the screen were over here, we would see it be destructive, constructive, destructive, constructive, destructive, constructive, or dark, bright, dark, bright, dark, bright, dark, that repeating pattern, that interference pattern. What's interesting is that this happens when there's two openings. Again, each opening serves as a source of light with these circular wavefronts that are overlapping each other. When you have a single slit, and I encourage you to do it on your own so you see it happen live and in person, we still get this repeating pattern. If we go across, this is bright, dark, bright, a lot of energy there, dark, and so on and so forth, that repeating pattern that we saw in the other image. But it's only from a single opening, and here's where Huygens Principle comes in. Huygens Principle said that every point on the wavefront, so here's the wavefront that's getting through the opening, acts as a source of tiny waves. So imagine a whole bunch of sources right here, or if this were a ripple tank, you're tapping the surface at all these different locations, and then each one creates its own pattern of circular wavefronts, and they overlap with each other. And so even with a single opening, we get the interference pattern. The next thing I would show you in class is what light looks like when it goes through the diffraction grating. With the other PowerPoint I showed you with the polychromatic or white light, this is what monochromatic light looks like. So here's the red light going through, and there's thousands of openings on this slide here. Here's the bright spot in the middle, and the next bright spot, and there's the middle again, and the bright spot. Here the bright spots aren't really blobs of light, they're really more like distinct dots of light with a whole lot of nothing in between. There probably are some bright spots in between these ones here, but they're so low in intensity the human eye can't pick them up. And so this is a very distinctively different pattern than we saw for the single slit or double slit, where the pattern for single slit or double slit were sort of tightly packed together. Here these dots are farther apart. Those were sort of blobs of light. These are dots of light. And it's just a different pattern here for the diffraction grating. Okay, so now I want you to have out in front of you your Snell's Law activity, and I want you to pause the video, take some time, read through the questions, form hypotheses, So we're going to be testing out Snell's law in a simulation instead of live and in person. Unfortunately, we can't do the activity we would in class, but we're doing a simulation. And so we'll be taking some data, plotting it on the graph. And so your first hypothesis as to what shape you think your graph is going to take. And at this point in the year, we've been doing this quite a lot. We know that graphs are linked to equations. And so you can take your best guess as to what shape that graph will be when you plot that data, manipulate it in that way. You'll also be taking your best guess as to what the slope of that graph should look like. I'm giving you a little bit of a hint though, right? Because we are taking the slope of the graph, so you should have a very good sense of what shape that graph will be, and then when you link it up to what equation goes along with this, you should have a very good guess as to what the slope should represent. And then we are going to be comparing some of our results to an accepted value. And so you can set a maximum percent discrepancy, and you know in the high school setting, we should never expect anything more than 30%. So you can certainly put under 30%, but I won't let you put anything over 30% because then you could totally mess up the lab and still get results that prove Snell's law. Okay, so just pause the video for a second, make your guesses as to the shape of the graph, as to what the slope should represent, and set a maximum percent discrepancy, then come back to the video. Okay, so you made your best guesses, and now you're going to read through the procedure, which obviously will be a little bit different from what we're going to do in the simulation, but I want you to get a sense of what would happen if we were to do the activity for real. I'll talk a little bit about that, then I'll show you what you do with the simulation. Okay, so if you're doing this for real, you'd have a piece of paper that looks like this with a protractor printed on it. This semicircle represents the medium you're testing, whether it's a dish filled with water or it's a semicircular piece of plastic. You're going to be over here in the air, of course, and light, we're going to pretend light is going through this medium and then out into the air towards you. And so you put a pin right over here, you put a second pin over here, somewhere in this region, and we're pretending light is going this way from one pin to the other. So your head would be over here, light would be coming from this pin to this pin in a straight line, and so we're visualizing light coming towards your eye, which would be over here. Which means the second medium is air. So we already know what N2 is. That's going to be 1.00. That's known. We're going to be trying to determine the medium index refraction of this medium. So we put another pin over here, somewhere on the curved side, so that if we were looking this way through the medium, light would be going through the medium out into the air, and it would appear to be in a straight line. But we know, of course, light will be changing direction because of the refraction effects. And when it comes to light, humans are stupid. So we think they'd come in a straight line through the medium, when in reality it would change direction. And so we're visualizing the light going from medium 1, which is either the glass or the water, this way, and then bending away from the normal, speeding up as it goes into the air. And if you were looking this way, all three pins, here, here, and here, would actually appear to be in a straight line because of the trick of the lights. Okay, so obviously we can't do all that for real. It would be great if we had time to. Maybe when we come back I can at least show you what it would look like. You'll be doing a simulation. So there's a link on the Google Classroom to what's called a PhET simulation that mimics this. I'm just going to lead you through some of the instructions. It's actually incredibly intuitive, and you're going to be taking the data and plotting the graph as if you did the actual experiments. So when you load up the PhET simulation, you'll get this menu here, and you're going to be clicking on the intro. You'll get a screen that looks like this. This is going to be our source of light, and here we can select different media. Right now it's set up to go from air into water. We want to go the other way. So click on this menu, select water, click on this menu, select air, and now we'll have the light going this way. Click on the red button that turns the laser on, and so here we have the light bending away from the normal, just like we expect it to do. We also have the reflected ray. Don't do anything with that. You can certainly verify the law of reflection if you'd like to, but you don't really need to. And then you're going to drag this protractor onto the screen. You want to line up the 90 degrees with the boundary, the 0 degrees with the normal, of course, because we measure angles from the normal. And then you just move the laser around to get different incident angles, and then measure the different refracted angles. So we're having light go this way, so that theta 1 is going to be here in the water, theta 2 is going to be here in the air, and yes, we're going to get perfect data, but still, you know, you may misalign the protractor somehow, you may have a slightly different interpretation as to what the angle is, and so we might get a little bit of a variation, and so maybe it won't be exactly perfect data, but it probably will be pretty good. Alright, so you just move the laser around. You want to get a variety of incident angles to measure the refracted angles as well. And then you just fill it in on the data chart that's provided on the activity. You manipulate it in the other two columns there where we already know N2 is exactly 1.00. You're going to plot it on the graph. And the instructions are right there in the activity as to what to plot. Now, I'm not giving you graph paper, but there is a link on the Google Classroom to a way to print free graph paper from the internet if you don't have graph paper at home. And then just follow the instructions. For the second medium, in class we'll be doing the piece of plastic, but you are just going to access here what's called Mystery B. All right, we don't know what medium this is, but you'll do the same idea. You'll move the laser around to different incident angles, take the data, measure from the normal for incident angle, refracted angle, manipulate the data, plot on the graph, and then you're going to be determining the index of refraction for this mystery medium, and then we'll go on from there. Okay, so get all that done for next class, get all the graphs done, get your slopes done. We'll do the analysis questions together. Look, if you want to get ahead and want to do the analysis on your own, that's fine, but really, just the expectation is you have all the data done, the calculations done, and the graphs done. Just follow the instructions. It's all there in the activity.